Good morning. In this video, we are talking about enthalpy change for a chemical reaction. So in the previous video, we tried to define what is enthalpy, and we also discussed the relationship between change in enthalpy and change in internal energy. So in this particular video, we are going to talk about how we can calculate enthalpy when it comes to chemical reactions. Okay, so to understand that, I have written here a hypothetical reaction where A and B are capital A and capital B are my reactants, and capital C and capital D are the corresponding products. And adjacent to them, I've written their number of moles. So the coefficients are basically the number of moles in the reaction. Okay. And so we have to derive an expression which we can apply even in the chemical reaction in order to calculate the value for delta H or delta U. So for doing that, we will use the expression that we originally started with, and that is the definition of enthalpy. So definition of enthalpy was H is equal to U plus PV. Now introducing the finite change here. So delta, delta H is equal to delta U plus delta PV. Okay. And so this is the expression that we started with. Okay. And we can easily calculate delta H and delta U because delta H is equivalent to heat change at constant pressure. At the same time, delta U is equivalent to the heat change at constant volume. However, how to calculate this particular term is the tricky thing when it comes to the chemical reaction. So we need to convert this into a format which we can easily understand in terms of chemical reaction. So for that, what we do is we will use the ideal gas equation, which is nothing but PV is equal to nRT. Okay. Now, this is what we have to find, that is delta PV. So it represents the finite change. So in this case, our final state is the product, initial state is the reactant, and therefore we can write PV product minus PV reactant. This is what we have to find out. And we know from the ideal gas equation that PV is equal to nRT. Okay, so applying this to the product, we can write, we know the number of moles in the product as C for this particular product, that is capital C, D for this product, that is capital D. So accordingly, we can write the corresponding forms. So we have CRT, C represent the number of moles of the product capital C. So it's CRT plus DRT for the product side minus the reactant side. It is ART plus BRT. Now, here you can see that R is a constant, so there is no variation in there. And right now, usually reactions are done at an isothermal condition. So this process is isothermal, and therefore we have a constant temperature. That's why in all this case, we are not changing the value of temperature. So we got this particular thing. Now, RT is common in all of this. So I'll take RT out. So I'm left with C plus D minus A plus B, okay, which is nothing but the change in moles of the product minus the change in minus the moles of the reactant. So these are the moles of the product and these are the moles of the reactant. So the difference is what we are getting from this particular expression. So in short, I can write RT as equal to, this as equal to RT delta NG, where delta N represent the change in moles of the uh, product versus the reactant. Now here I have used a subscript G to indicate that if suppose in this particular reaction that I have considered here, all the components are gaseous state. Suppose you have in a reaction, some as liquid, some as solid. In those cases, you do not include their moles here. Here we only take those reactants and products which have a gaseous state, and that is why I've mentioned in here. Okay, so and therefore now we can put the delta PV as RT delta NG, and so now this equation that we started with can be written as delta H equals delta U plus RT delta NG. This is a very, very important expression in order to calculate heat changes that are happening in a chemical reaction. Okay, so let me take you to the what do you say, a question which would elaborate the application of this particular equation. Okay, this is very, very important, and I hope you have understood the derivation or how to understand this equation, not exactly a derivation, but just how this equation came into being. And this you should keep in your mind. All the equations that I have kept under box, please make sure you are able to understand how we reached each of this equation, because it will help you. Because it will help you to also solve the numerical, and if some derivations is asked, you should be able, or not exactly derivation, some relationship is asked, you should be able to give proper explanation. Okay, so now let's look at the question here. So in this particular question, what you see is the heat of the reaction at constant, the heat of the reaction at constant volume is given to be minus 88.5 kilojoule at 298 Kelvin. Okay, calculate the heat of the reaction at constant pressure. Okay, so we are given heat of the reaction at constant volume. So that means QV is what is given. And we know QV is equal to delta U. And that value is given out to be minus 88.5 kilojoule. And what we are given is temperature, 298 Kelvin. We are asked to calculate the heat of the reaction at constant pressure, that is QP, or it's equal to delta H. So this is what we have to calculate. So this is for this reaction is what we are going to calculate the enthalpy. Okay, so the formula that we use is this particular formula, which we just now looked into how to derive that. And therefore, this formula is delta H equals to delta U plus RT delta NG. Now, delta U, we already know the value, and R we know in SI unit in joules, it should be 8.314 joule per Kelvin per mole. Now here, it's kilojoule, therefore I have included this conversion factor, that is 10 to the power of 3, to convert it into joules. And T is nothing but equal to 298 Kelvin. Now delta NG, now here in the product side, you have two reactants, okay? But H2 is in liquid state, so you don't consider the number of moles of the water. So we are going to only consider carbon dioxide, and therefore the product mole is 1 minus the reactants. So reactants, CH4, 1 mole, O2, 2 mole, so 1 plus 2. So 1 minus 3, that comes out to be minus 2, because this is the negative, higher value is the negative value. So it is minus 2. So accordingly, you will put that here. Okay, and when you calculate, you get a negative value here. then this is negative, both will add on to give you this particular value for the delta H. So this is how you should proceed given any reaction to calculate the respective terms in this particular equation. I hope it is clear to all of you. Thank you and have a nice day.